Everyone, my name is Fardin Bahreini. My supervisor is Dr. Amin Hammad, and my research topic is toward an ontology for BIM-based robotic navigation and inspection tasks. Let's start with introduction. Inspection robots are used to automate the process of inspection during the construction and operation phases. Moreover, robots can be equipped with scanners or sensors to make the inspection process more accurate and reliable. In this regards, autonomous robots need to deal with high-level semantic data along with low-level sensory motor data. Ontologies suggested to support the robotic process by providing a central data store. Moreover, the BIM-based approach is expected to improve the inspection process as the BIM model contains accurate geometry and relevant information of a building. Regarding the different life cycle phases, BIM models include as designed, as built, and as is model. Let's take a look at problem statement. Robotic inspection needs to be integrated with the knowledge of the construction domain to be more effective and efficient. Besides, a clear and accurate description of the surrounding environment and the task can help the robot to perform the task more autonomously. The objective of this paper is developing BIM-based ontology to cover the different types of information and concepts related to robot navigation and inspection tasks. The ontology is called Overneath Ontology for BIM-based robotic navigation and inspection tasks. Let's move to the literature review. I want to explain inspection tasks during the construction and operation phases. Lack of proper inspection during the construction phase will increase the cost of maintenance in the operation phase. Moreover, facilities need regular inspection to satisfy their predetermined function. Finally, post-disaster inspection should be done in the event of a disaster and before reoccupying the building to evaluate the potential hazards. Let's take a look at using robot for inspection. Industrial cases shows the variety in types, capabilities, and uses of robot for inspection. Moreover, mobile robots are designed for sensing, navigation, inspection, and remote operation in dangerous situations. Also, service robots can be used for different purposes in the AEC/FM industry, for example, cleaning purposes. The picture shows two examples of industrial robot. The first one is a spot which can be used for sensing, inspection, and remote operation. The other one is a filler back bot which can be used for remote inspection and remote operation. The other aspect is BIM and navigation. And path planning in 3D spaces need information related to spaces and their function, geometry, location, obstacle, and accessibility of spaces. Moreover, BIM can help to extract accurate and up-to-date semantic and geometrical data. The logical network is a representation of the full 3D building model and a detailed navigable network. For example, spatial relationships between floors, rooms, and shared walls. This figure shows the visualization of path planning in the BIM model. Let's take a look at ontology approach. In the robotic area, ontologies can be used for different applications such as general robotic purposes, for example, standardization, or ontologies for autonomous robot. This figure shows the NORAP ontology diagram, which a robot can use OWL ontology along with common sense knowledge and action-related knowledge. Let's move to the methodology. The methodology used in this paper is methodology, which is an approach to provide a structure for the ontology at knowledge level. Moreover, methodology deals with the life cycle of developing ontology. Overneath developed based on methodology include the initial, development, and final stages. The initial stage involves the step to specify the scope, main concepts, and the taxonomies of Overneath. The development stage is devoted to constructing and verifying the initial structure of Overneath. And the final stage is to add new or modify existing relationships or evaluate Overneath with expert and end users. Let's take a look at developing Overneath. Robotic inspection is integrated with the knowledge of the construction domain in Overneath. Moreover, the developed ontology covers 4 main types of concepts, include robot concepts, building concepts, navigation concepts, and inspection concepts. Overnet is developed using Protege, which is used to create, display, and process the ontology information. Ontology integration is done to reuse and adapt the concept from building element ontology, which is based on the IFC building element subtree in the IFC specification and existing IFC OWL ontology. The types of relation used in the developed ontology include is, has, uses, affects, performs, and so on. This figure shows main concepts and relationships of Overnet. As you see, there are four main types of concepts. Building concepts include concepts related to BIM and mismatch. BIM concepts cover concepts related to building element, furniture, temporary structure, distribution element, and so on. The mismatch concepts cover information related to mismatch between as designed, as built, and as is a state of surrounding environment, missing object, unexpected object, non-conformity issue, and so on. The navigation concepts cover information related to node, link, path, and other concepts related to navigation task. Also, the robot concepts cover information related to robot movement, constraint, obstacle for robot type, robot size, robot sensor, and so on. This figure is continuation of the previous figure. The point of interest for the inspection task is defined based on the inspection purpose, which can be general scanning, inspecting HVAC systems, or detecting building defects. Also, the other concepts that could be covered in the inspection tags are inspection method, collected data such as image, point cloud, and so on. Let's move to the case study. This is a hypothetical case study of using an inspection robot to find the leakage in building at Concordia University. The assumption is that the robot partially knows the environment, and in case of finding an obstacle, the robot must replan its path. Inspection point of interest is on the 9th floor. The BIM, this is the BIM model of Concordia building, and the robot can use one of the elevator to access the 9th floor. The second part of the path is the horizontal movement from 9th floor elevator hall to the room 9215. The shortest path, which is path A, follow these nodes. However, this path is blocked with scaffolding, which are used for a renovation project and create an obstacle for robot. Therefore, robot must follow a longer path, which is path B, and follow these nodes to reach the room. The last part of the path is the movement inside the room from the door to the destination node, which is the point of interest. And finally, this figure shows the robot collecting images of leakage in the room. The case study demonstrates that Overnet can cover all the concepts necessary for the planning of robotic building, navigation, and inspection. The table shows example of these concepts, and in future, a software can be developed with extraction of all required concepts from developed Overnet. Let's move to the conclusions. Overnet comprises high-level knowledge of concepts and relationships related to building, robot, and navigation and inspection tasks. BIM is considered as a reference that is integrated with the knowledge model, and the application of Overnet was evaluated in a case study, and based on evaluation, Overnet was able to give a clear understanding of the concepts and relationships in the domain, and it can be applied for developing robotic inspection systems. The main contribution of this research are Overnet is able to capture the essential information from BIM, which can help to develop a seamless knowledge model to cover the missing parts of BIM. And also Overnet can be used as a first step toward logic-based inspection, which can help the robot to perform the inspection task autonomously without the help of human judgment. Future work will focus on further development and implementation of Overnet to integrate it with low-level robotic capabilities to make the robotic more autonomous. And the abstract knowledge can be combined with robot action-related procedural knowledge to make the task executable. Thank you for your time and attention.